Good evening, everyone. Welcome to the first episode, Season 2 of Kaggler's Talk. I am Snigdha from ML4E NIT Rourkela. Today's webinar is based on the ventilator pressure prediction problem by Google Brain on Kaggle. We have with us Nikhil Kumar Mishra, currently working as a data engineer at Karma Life AI, and his teammate Sahil Verma, ML engineer at OK Credit. Firstly, I would like to congratulate both of them for achieving fifth rank in such a prestigious competition. Today, they'll be sharing with us their approach on the problem statement and will also be giving us some insights on how to handle such problems. Over to you, sir.
Thanks, Nikla, for the introduction. So I'll start by sharing my screen. Yeah. So just a brief about myself, and maybe Nikhil can also introduce himself post that. So hi, I'm Sahil. Currently, I'm working as a senior ML engineer at OK Credit. Uh, uh, and yeah, that's about me. So Nikhil.
Yeah. Hi, everyone. I'm Nikhil. I'm currently working as a data scientist in a startup called Karma Life. So, yeah, maybe Sahil can continue.
Sure. So I hope you guys can see the screen. So we participated in this competition, which was organized by Google Brain, and the competition name was Ventilator Pressure Prediction. We participated as a team under the team name of CR7 is the GOAT. And in case you want to go through a detailed solution summary, wherein we try to explain each and every point in detail as much as possible, there is a link here. We'll be sharing the PPT with you guys if that would be possible. If not, if we can share the link in chat, that would also be helpful. Yeah, cool. So let's start with the problem statement. The objective of the problem was to predict the airway pressure in the respiratory circuit during the breath. So what is a respiratory circuit? So the diagram shown here is essentially what a respiratory circuit is. Um it's what a ventilator might look like. There is an inspiratory phase. So there is an air source which lets the air in, and there is an inspiratory valve which basically controls how much amount of air is going into the lung. And then this is connected to a lung, and the output is being controlled by another valve, which is the expiratory valve, and it controls basically how much amount of air is flowing out of the lung. So this is what an entire respiratory circuit look like. And our target was to predict how much pressure would be there in this entire setup when the air is flowing in through the system. So apart from this, we were given a set of control inputs and certain lung characteristics, which we'll expand on later. So this is what the input data looks like. I'm assuming that some of the columns would be visible. So the data set comprised of different breaths. So when we take a single breath, so we were given different kinds of breaths of each lung, and the breath length was around 3 seconds. We were given 3 seconds of breaths. So you can see certain IDs, the ID and the breath ID, which basically helps us identify when one breath starts another and when one ends. Apart from that, there were certain lung characteristics which were shared with us. R and C were the variables that corresponded to the lung characteristics. And these variables essentially control how the lungs, different kinds of lungs would respond to the influx of the air. As like each lung would behave differently when the like it would expand differently, and the pressure profile would be very different as in when the air is flowing in. Now, UN is the control variable which was provided to us, and essentially it is the percentage of the air. It is a control variable that controls the percentage of the valve that is open. And by controlling the valve, you are essentially controlling the flow of air into your lung. So into the lung. So essentially, you can see it as the amount of the volume of air that is flowing in some way. And for the expiratory wall, we were not given a continuous spectrum of values for u out. Rather, we were just given an indicator variable, which showed that whether the air was flowing out of the lung or it was just or whether it was not flowing. So basically, if the value is zero, that means that the air is not flowing out. It is just getting collected inside the lung, and which also corresponds to the inhaling phase when we breathe. And similarly, when the value is one, that means like the inhalation is complete. Now the exhalation is starting, and the value of u out equal to one indicated that. Now, as I mentioned earlier, we were given a set of breaths. So we had roughly around 75,000 lung simulations. When we say lung simulation, these were 75,000 breaths in the training data set, and roughly around 50,000 breaths in the test data. Cool. So this was a brief about the data set, like what did the data look like? Uh, yeah. Now, this is how we plan on covering our solution. So this is a gist of different components that we have, like the key points that we have in our solution. We'll go over each one of them in detail and try to explain as much as possible. So the first question was like, as mentioned earlier, we were given breath level data that like one breath had around 80 data points, like 80 timestamps, and using those 80 timestamps, you could visualize how one breath would look like. Now, the first question was, do we really need the entire all those 80 timestamps? Because one more caveat there was that the score that was being like the metric that was being calculated was only calculated during the inhalation phase. And one of the reasons I believe that this could be like why did the organizers keep it this way, that the scores are only evaluated on the inspiratory phase, was because if you try to visualize the pressure profiles or the basically the UN profiles of your expiratory phase, it it didn't change much across different simulations. So more value, like it would be more valuable if we would be able to like build like forecast or predict pressure profiles in the inspiratory phase. So yeah, so the evaluation was only done on the inspiratory phase. Now, knowing this fact, we tried a couple of experiments. Like we tried to see that what is the maximum sequence length in the inspiratory phase. So, for example, my breath would be very different from Nikhil's breath. Our breathing capacities would be different, and the time or duration during which we would be inhaling would also be different. So I might breathe in like for let's say 1 second, whereas Nikhil might be breathing in for like 0.75 seconds. So we had variable inspiratory phases across different breaths, but the maximum length was around 35. So what we decided to do was like if the maximum evaluation that could happen for any given breath would be on a length of 35, why not just work with a length that is closer to that and remove the rest of the data? So that is what we decided to do. We decided to work with a length of 40. That means when the breath starts, we only take the first 40 timestamps to build out our models, and we just check the remaining data. And as expected, like our hypothesis was the performance should not deteriorate much. And post this experiment, we saw that the performance we were getting using the entire 80 timestamps versus the performance that we were getting only using the 40 timestamps, it was comparable. So now, since the performance is comparable, the major advantage we got through this was that training times became significantly shorter. It almost reduced by half because we were working with a lot less data. And as a result, we were able to do more number of experiments, iterate faster, which I believe is like one of the crucial aspects of when you are participating in a competition. Do not stick to one idea, but rather in the initial phases of the competition, try to experiment as much as possible, and later on you can have a more narrow approach and work on things that are giving you good results. But since so because of this, like shorter training times, we were able to experiment more, and we were able to train our models for longer. So, one of the key ingredients of our solution is that we trained our models for we trained our models for around 1,000 epochs. So yeah, that was possible partly because of this. Cool. So now we'll move to how we set up this problem. So, as mentioned earlier, since the output variable is a pressure profile, on the surface, it looked like, uh, not on surface, it actually could be seen as a regression problem because the values seem, output values, the pressure profile values seem real value. And we also started out solving this as a regression problem. But post like digging deeper into the data, what we realized was that these pressure values were discrete in nature. Like for all those 75,000 breaths that we had in our training data, there were only 950 unique values of pressure. And these were also separated by a constant difference. For example, those 950 data points, if you just sort them and you just calculate the difference between the subsequent pressure values, you could see that there was a constant step difference. So this gave us an idea that why not convert this to a classification problem and try to solve this. And that is what exactly we did. So there are a couple of approaches that you could take here. So there's a classification route and there was an ordinal regression route. We tried both of them, and we'll try to explain in detail in the later on slides, like which worked better. But so what we saw that the classification approach was giving us better results, and not only better results, the convergence of the model was much faster. And uh, because of this convergence being faster, again adding on to our sequence length idea, we were able to iterate. Like this also helped us increase our like the number of experiments we could do because we could get uh, results faster. The convergence was better. So yeah, we formulated this as a classification problem, and we tried a bunch of different losses here, and we also tried ordinal regression, which we'll cover later, like what all losses we tried. So yeah, over to you, Nikhil.
Yeah. Uh, Thank you for the wonderful introduction, Sahil. Yeah. Okay. So, firstly, we'll be talking about validating things. So, what is validation, right? So, whenever you train your machine learning models, you basically need to have something to test your model on, right? So, you don't usually use all of your data to train the model, right? You keep some part of your data separate for testing the model. So, what we did in validation was we used k-fold validation. So k-fold validation is nothing but say splitting the data into k different parts, right? So when you split the data into k different parts, you can do is you can take one part out for testing and combine rest of the parts and use it for training the model, right? So like you can see in this diagram, I have split my data into five different parts, right? So what happens in the fold one is that I'm using A, B, C, and D for training and E for validation. Similarly, in fold two, I'm using D for validation, and then we go on to C, B, and A, right? So, what is the advantage of key-fold approaches? Basically, we can combine our predictions and get out of folds, right? So, what is out of folds? Out of folds is the predictions on all of your data, right? So, basically, you get some estimate of all of your data, right? Some prediction by the model, right? So, you can use it later in ensembling, right? So, in ensembling, we basically have, say, some kind of meta models, right? So, in your meta models, you feed your out of folds and your predictions for the test data, right? So like if you see the rightmost column, I have test spreads, one test spreads, two test spreads, three test spreads, four, and test spreads, five. So these are basically the predictions on your test data for five different models. So here it's written mean test predictions, but yeah, the metric for the model was mean absolute error, right? So for mean absolute error, it will be better if you take the median of the predictions instead of the mean, right? Okay. Sahil, can you move on to the next slide? Yeah. Okay. Talking about feature engineering, right? So, firstly, this was a typical time series kind of problem, right? So, when you have time series problems, you have data at say different time steps, right? So, when you have data at different time steps, you can use some classical time series feature engineering methods like say shifted features. So, what is a shifted feature? Say basically, if I have a feature at time step t, Then I can also add feature at time step t minus 1. I can also say add a feature at time step t plus 1 for the same variable, right? So basically, I'm saying that if I have un for sequence of current sequence which is of 30, I can also add the un what which was at say sequence 29, and I can also add un at sequence 31, right, as different features, right? We can also have window features, right? So a window is say a fixed say basically you can imagine windows as say a fixed length sequence which you keep iterating in your data. So basically, if say if I have a window of 3, I can aggregate my feature at time step t minus 1 and time step t minus 2, right? And then I can use the aggregated statistics as some kind of feature. So basically, I could say use the average value in the past 3 time steps, or say the maximum value in the past 3 time steps, right? So even we can use that as a feature, right? And then we also had cumulative features, right? So basically, one cumulative feature that was helping a lot was the cumulative un, right? So what is a cumulative feature? You basically keep on aggregating the feature till the current sequence, right? So basically, a very simple example would be if you have if I want to do a cumulative sum, if I have say values of say 1 2 3 and 4, so the first value will be 1, the second value will be 1 plus 2 which is 3, the third value will be 1 plus 2 plus 3 which is 6, and then we'll have a last value of 10, right? So these are classical time series features. And if you have participated in the competition, you might have also seen it in the public kernels, right? Similar kinds of features. So our feature engineering was no different than the public kernels. Second thing is learnable front end, right? So this was a very crucial feature in a final model architecture. So what do you mean by a learnable front end, right? So if you have used cnn's for images, you know that cnn's can act as good feature extractors, right? So they can extract useful information from your data, right? So if your data is say unstructured, something like an image or text, right? So for image, we use 2D CNNs, but say if we want to apply the same CNNs for time series problem or say for text data, we will have to use 1D CNNs, right? So what do CNNs do? CNNs capture your neighboring information, right? So basically, say if I was applying a window feature, what I was doing was, say I was aggregating the past 3 values, right? But then there I was applying some fixed kind of aggregation, like say mean, median, max, or mode, or whatever, right? But what CNN helps us to do is they automatically decide what they want to learn, right? So it could be some crazy combination like 3x plus 4y plus 5z, right? So something like that, or say something even more complex. If you say want to aggregate the 3 nearest neighbors, right? Or if you want to go 5, you can go 5. If you want to go 7, you can go 7, right? So the biggest advantage of CNNs is they decide on their own how you know collect the information from the neighboring data and use it to add value to your model, okay, right? So if you have also seen it in past audio competitions on Kaggle, a lot of CNN was used, right? Because then again, uh, yeah, uh, audio data is also some sequential information, right? And then you can use CNNs to capture neighboring information, right? Right. Okay. Sal, can you go to the next slide? Yeah. Okay, so this is how our learnable front end looked like. So what we did was instead of using only one CNN with fixed kernel size, right? So kernel size, or say if you can say it window size, right? So instead of using one fixed window size, we basically did was we tried multiple window sizes. So the intuition behind this, right, is something like you don't only want the very closest nearest neighbors and collect information. You also want to kind of go far and then collect the information, right? So say if I'm using a window length of 2, my window is just looking at the next nearest neighbor, or so which is the neighbor which is just previous to the current data point, or which is just next of the current data point. But say if I want to if I take a window size of 7, then I'm looking at its 7 nearest neighbors, right, in sequence, right? So what we did was we basically used kernel sizes of 2, 3, 5, 7, 11, and 15, right? So this helps us capture both nearby information and kind of information which was far away from the current sequence point, right? And then we had out channels, right? So basically out channels is basically the number of filters, right, or the number of different combinations you are learning, right? So this was the learnable front end, right? So this gave us total 96 features from CNN. Then we combined it with the original input raw features and the time series features that we had created, and then we fed it to a model. Sal, can you go to the next slide,
Cool.
please?
Just a couple of things there.
Hmm.
So, yeah. So, as you can see that we tried out these filters, like starting from k equal to 2 to k equal to 15 by skipping some in between. These are really just hyperparameters. For example, these worked out for this set of problem. Now, if you are working on, let's say, an audio problem or a different problem, you might want to iterate on this. This is like one of those hyperparameters that you play around with. And similarly for the out channels, this is something, uh, even in our case also, there could be a better possible learnable front end. So we'll also dig deep on the kinds of front end that we could have here, but these didn't really work out in this competition. But again, the number of output channels is something, is also an hyperparameter, and you could also iterate on this. Yeah, cool.
Okay. Okay, so finally we come to transformers. So transformers was the magical thing that happened to us, right? So yeah, we'll be covering later on the different types of architectures we worked with, but then again, transformers really help. Uh, yeah. Okay, so basically, Sal, can you just go back to the previous slide?
Yeah.
Yeah,
Yeah.
sure. So if you see a typical transformer, it has both an encoder as well as a decoder part, right? So but we only use an encoder structure. We did not get time to experiment with the decoder structure, right? So if you see a typical encoder structure, it will have your input embeddings followed by multi-head retention. Then you add and apply some normalization. Then you'll have some feed forward part, and then you apply, add, and uh, do some normalization, right? So transformer layer is quite complex to explain for this webinar, but yeah, I would encourage everyone to just go and look at it, right? So if you just stack multiple encoders together, you encoder layers together, you can have a stacked encoder transformer, right? Then in the output you can have, say, some kind of layer which will help you, say, predict your 950 classes, right? uh, Next slide, please. Asal, can you go to the next slide? Yeah.
I
Okay.
already moved. Yeah.
Yeah. So, okay. So I'll just quickly talk about the main components of our transformers, right? So our transformers were highly parameterized and regularized deep transformers, right? So just let me tell it in some simple sentences. So highly parameterized means it basically had a large number of parameters, right? So if you want to understand it in terms of simple neural networks, if you have a neural network of, say, only one layer and it has, say, 5 neurons, uh, you could learn less compared to if your layer had, say, 5,000 neurons, right? So 5,000 neurons has a better learning capacity, because you can have different more number of combinations, right, of, say, your features which is coming from the previous layer, right? But one big problem with highly parameterized networks is that they overfit fast, right? So when you have a large number of things which you can learn, right, your model will try to come as close close to the training data as possible, right? So basically, your model will try to overfit to the training targets, right? So to overcome this, we'll have to have some kind of regularization method, right? So for the regularization method, we had to use dropouts, right? So yeah, one thing before we progress further was, this was one of the other reasons why we could not use regression, right? Because we were dealing with score differences at the scale of 0.01 and 0.001, right? So in this cases, if you use regression with dropouts, firstly, regression with dropout does not work as well as compared to regression classification with dropouts, right? So regression has some kind of normalization which will not propagate easily if you use dropout, right? So yeah, this was one of the main reasons why we use classification instead of regression, right? Now, how do we over parameterize the transformers? We can increase the number of heads of the transformer, then we can also increase the number of layers of the transformer. So by increasing the number of layers, I just means you can stack transformers encoder layers on top of each other, right? So on the output of one encoder, you can just put another encoder, and then you can go as deep as you want, right? So having a very large number of heads was the key for us. We had 128 different heads, right? So having more number of heads again just helps you learn more number of more number of, say, representations of your data, right? Yeah. So one more thing that we tried out was RE0, right? So RE0 is a paper in which they have described to train deep neural networks what you can do with residual connections. What you basically do is, instead of simply adding the output of the previous layer and the current layer, what you do is you add you take additional parameters, say alpha, right? And then you multiply it with the output of the current layer, and then you add the output of the previous layer. So what it does, it helps the network decide how much of the current information you want to retain before moving forward, right? So this is a kind of alternative to the simple addition in residual networks when you just simply do a plus b. Instead of a plus b, we are just doing alpha into a plus b, right? So alpha is another parameter which is learned by the model. So if you read the RE0 paper, in the results they have described that this really helps speed convergence of deep neural networks, right? Especially transformers, right? Okay. And then like high dropout to combat overfitting, right? So we started with a very low dropout, right? So when we are starting with the transformers architecture, we saw that it was overfitting, right? After we highly parameterize our transformers, right? So then we started adding a little bit of dropout. We started with a dropout of zero point zero 0.05 and then 0.01. And then we saw that in our experiments, it was helping us combat the problem of overfitting, right? So by that, I mean that the validation loss and the training loss uh, had a less difference in their scores compared to if you use no dropout, right? And then as and when we over parameterize our model more, we kind of added more and more dropout, right? So at the end, we had a dropout of actually zero point 0.8, right? So that basically means you're dropping it, your dropping chances are 80%, right? So which is really high for any neuron. But then again, it helped our model, right? So yeah. So basically, to add dropout or any kind of regularization technique, the best thing you can do is you can look at your training losses as well as your validation losses, right? So if your training loss is decreasing rapidly but not a validation loss, you can combat it with the help of regularization, say such as dropout, right? Now, a very interesting part of a solution was we added 1D convolutions. So this 1D convolutions is not the same as the 1D convolutions we are talking in the input features, right? So when we were creating our input features and then we added 1D convolutions and combined all the features. Here, this 1D convolutions is basically being added to the output of the encoder layer, right? So previously we talked about encoder layers being stacked on top of each other, right? So how do you stack encoder layers, right? So the output of one encoder layer goes into the second encoder layer. Then the output of the second encoder layer goes into the third encoder layer. So instead of just feeding the output of one encoder layer, we concatenated the output of the current encoder layer, also convolutions applied to the output of the current encoder layer, right? So what attention mechanism is doing is it's basically combining one sequence point to all the points, right? So it's kind of using the global information. So to combine global information as well as local information, what we did was we added convolutions to the output, right? So when we merge convolutions as well as the output of the transformer encoder, we get local information as well as global information, right? So I think this idea has been around for some time, right? So yeah, maybe Sahil can say talk about conformers, right? So Do you
Yeah.
want to
So a
say?
couple of points before that. So
Mhm.
we have always heard about this notion that if you have a data set of, let's say, 1,000 data points, or let's say 5,000 data points, um, it is better not to build a neural network model on top of that. And the reason that gets quoted is that because of the high number of parameters in the model, in the neural net models, it might overfit. The model might have very high variance. But you can clearly see that if you are able to correctly regularize your model, if you are able to penalize it enough for your overfitting that is happening because of the large number of parameters, you can even train a very large neural network model even on a very small data set. So just to give you some context, that a BERT transformer layer, I guess, has around 12 layers. This model had 20 layers, and the number of heads that we have there in BERT, I guess, are six. I'm not sure of the exact configurations, but around we have six heads there, and this model had 128 heads. So you can clearly see that even though the data set is very small compared to the corpus on which we train our NLP models, but we were still able to achieve very good results using this highly parameterized models, and all of this because of the high dropout values we have. Like zero point 0.8 value is something that we generally never hear of. We are almost dropping all the information that is being passed through our network. And yeah, and our neck like this was an internal joke that was going on within our team, that if we continue on increasing the number of layers, we might end up reaching dropout equal to one. Like we were increasing dropout at such a rapid pace. Now coming to conformers, as we said earlier, that this competition, you could say, it's a time series problem, and audio classification, or basically audio processing, is something which has recently picked up, like with a lot of pace for the past 2 3 years. And you could see that most of the SOTA algorithms on those audio classification or basically audio processing ASR problems are CNN dominant. Like most of them would have some component of 1D CNNs. So conformers is another one such architecture which currently gives almost, I guess, it's close to the state of the art in automatic speech recognition. And the underlying building block of that conformer block is it has a multi-head attention layer combined with your 1D convolutions. So again, we tried to we got inspired from the same idea that since we are working on a 1D time series problem and we are using transformers, like why not add conformers also? So this was like the idea that like the inspiration behind why we tried 1D convolutions. Yeah. So I'll
Yes.
move to the next slide, Nikhil.
Yes. Yes. Okay, so this is basically how our final model architecture looked in a nutshell, right? So you have the numerical features, you pass it to the 1D CNN layer, which creates more features, and then you combine your numerical features with the 1D CNN layer outputs. You also have the categorical features. I think I forgot to mention about it. So for categorical features, you basically use categorical embeddings, right? So we had an embedding layer. So uh, the output of the CNN, the output of the embedding, and the raw input features were combined, and we had some transformed input, right? And then we passed the transformed input to the transformer plus CNN layer, right? So in a nutshell, our transformer had 128 heads. We had 20 encoder layers, right? And the output of each transformer layer was passed to a 1D conf, which had a kernel size of 3, right? So we are just capturing informations with window size of 3, and then we had 16 kernels, right? So you can think of it as 16 more features to the next transformer encoder layer, right? And then we had two phases, in phase and out phase, right? So yes, I think we forgot to mention about it, but basically it is basically telling the model to treat the input phase and the output phase separately, right? So the input phase is nothing but the inspiratory phase where you breathe in, and the output phase is nothing where you breathe out, right? So basically we are using two outputs, one output to predict the inspiratory phase, one output to predict the expiratory phase, and then we combine the outputs, right? So if you had participated in the competition and you had done some EDA, you can quite easily see that the output phase is kind of hard coded, right? So it could be better if we help the model, you know, distinguish between the inspiratory phase and the expiratory phase. And even doing this helped our model score in the last time of the competition. So yeah, we stuck with it, right? So we are thankful to one of the Kagglers, Heng CK, who had posted this idea on the discussion forum. Yeah. Can you go to the next slide, please? Okay. So yeah, the final model was trained on 15 different seeds, right? So yeah, uh, just to make a distinction between seeds and folds, when we talk about seeds, we train on the whole data, right? So then again, you might question, as just told me in the beginning, that we keep some of the data for validation purposes and then you train on rest of the data, right? So why are we training on the full data? So basically the idea is, if you have an estimate of where your model converges, right? Or say if your say if your model is converging at around 1000 epochs, then you can basically train your model on the whole data for 1000 epochs, right? So you can have one validation set and training set first to just check the performance of model at 1000 epochs, and then you can train the same model for 1000 epochs on the full data, right? So why do we even try to train the model on full data? It's because it simply gives the model more data to train with, right? And that we clearly saw in our experiments, that if you added more data to the model, or say provided more data to the model, the performance of the model improved, right? So one more thing that we wanted to try out was pseudo labeling, but we could not try it, right? But then pseudo labeling also helps you provide more data to the model, right? So training on 15 different seeds is kind of similar to, say, bagging, right? So you train on different shuffled versions of the data, and then you combine the predictions, right? So you can combine the predictions by, say, taking median across all the different seeds, right? Yeah, so the CV was, say, around 0.105 to 107 when we ran it for a single fold, right? So we firstly did 15-fold validation. We saw our scores, and when we were sure that okay, we can train a model for 1000 epochs, we did that. Okay, so yeah, we had 1000 epochs, and yeah, a model I think did not even converge at 1000 epochs. So we could have trained our models for more epochs, but then we are also constrained by the time it took to train our models, right? So we stuck at 1000 epochs. Yeah. And finally, talking about our scores, we had a private LB score of 1022, which was 0.0999 in the public leaderboard, right? Do you want to add anything, Sahil?
Yeah. Couple of things here. So you might see that we have consumed a lot of resources here. Like we trained our model 15 times on different shuffled versions of the data, and we even tried 15-fold validations. Like why not just a 5-fold validation? Now, in case of competitions, most of the things are like you are competing for that last mile optimization. You have differences which are like of the order of zero point zero 0.001. So in order to cover that, whatever works best for you, for example, in this competition also, we started with the 5-fold validation scheme, but what we found out was that increasing the amount of data in each fold helped increase the CV score as well as your LB score also. And that is how we came to this number 15, and we could have also gone higher here, like to achieve better CV and LB scores. More number of folds would have also helped here. But the idea is not to have this number as a key value in mind, like 15 will always work. Generally, if let's say you are building out this model for actually deploying or in the production environment, you won't be deploying 15 different models, like 15 models trained on 15 different seeds. That is not like the amount of boost that you would get from that is not, like, you cannot justify it by the incremental computation cost that you would incur. So all the things that you see on this slide should be taken as a caveat that these were solely driven by by the objective of getting that zero point zero 0.001 boost. So that is one. And second thing is, so why uh, so in this case particularly, even training on the same data, but just the shuffled data, um, was like an ensembling that like 15 different models built on shuffled data give us good amount of boost on the LV. Now, why this was happening was, so this is particular to neural networks also. So there's this thing called snapshot ensembling. Um, if let's say you are training your neural net models, and there's this LR scheduler wherein you decrease your LR, you basically allow your model to converge. Then you suddenly introduce a spike in your learning rate so that model comes out of that local minima in which it is, and it goes to some other like some other place on the loss manifold, and it you start reducing the LR again, so it will start converging again. Now, by doing this, what essentially you are doing is you are finding different local minimas in your loss manifold. And basically I'm explaining what snapshot ensembling is, and essentially this is another way of doing that only. So in that way you would be having different, so your networks would be corresponding to different loss minimas on your training manifold. And especially in case of neural networks, if you then take the average predictions or bag these different manifolds, it actually gives you a significant performance boost. Now, this significant term is again from a competition standpoint. It might not be from a production environment standpoint. The boost might not be that significant, but this is a very common technique when you are training, let's say, our neural networks. Snapshot ensembling is very commonly used there. So instead of tweaking the LR and coming to a different local minima, we just thought that why not rerun your neural network models on different, like with a different seed, with a different, like with some shuffle in the data. Essentially, you would be ending up having the same effect. That is, you would be having different local minimas for each of your network. So surprising thing is, if you try the same thing, let's say we built a boosting model instead of a neural network model, and we just change the order of the data, we just shuffle the data, the boost that you would get would be really negligible. So this is something that the snapshot ensembling thing works really well for the case of neural network models. And in most of the winning solutions, you would find this trick that people use in case of neural networks. Yeah. So finally, we come to the things that did not work in this competition. And essentially, these are the things that you should always keep in mind, because these things did not work in this competition, but they might end up working in some other competition. So like this, in terms of the value add to the solution, I would say these things don't add any value, but these are the things which led us to that solution. So a couple of things that we would like to talk about are augmentations. So the idea again behind augmentations is to regularize your model, again to try to make your model more generalizable. Uh, so the best form of regularization that you can give to a model is to add more data. And since we did not have more data, we thought, why not try augmentations? So a couple of things that we tried in the augmentation phase was, we tried to add some noise to the input signal. That is, add some amount of Gaussian noise to your input uh, UN values, and see if there is some boost in the performance. Apart from that, we also tried some shift or flip augmentations. These are essentially like you were given timestamps from 0 to 80, you just flip the sequence and see if the model captures something which is very different. Uh, Surprisingly for us, this did not work out, but one of the solutions, like I guess another gold medal solution, used this flip augmentation trick and it worked out fine for them. But the idea was they implemented it in a slightly different manner from what we implemented, like how we implemented it. But the idea was the same. The core idea was they just flipped the entire sequence and trained their model on that. Now, coming to another idea, which was again this was a theme which was discussed in most of the top solutions. Most of the solutions did a multitask training. Now, what is a multitask training? Currently, we had one target. Now, but for a given problem, you could have more than one target. For example, uh, a very common example could be if you are given a face of a person. One objective could be you have to determine the age of that person using that selfie, and the other could be his expression, basically emotion. So these are two targets, and basically these are two tasks combined into a single problem, and we could solve them using a single network, which is solving for both of these purposes. So this is what a multitask learning is, and we tried to basically do some form of multitask learning using RNC values. So our hypothesis here was, since RNC basically define a configuration of a lung, and adding that value, let's say if our model also learns how a particular, basically the characteristics of a lung, how one lung is different from another lung, maybe that would help us get better pressure profiles, like it would help us boost our scores. But this did not work. uh, Now, how did other winnings team apply like this particular idea? Was that they did, instead of, like, we tried using RNC as auxiliary targets. What they did was they took pressure delta. Basically, you have your pressure profile, that is P1, P2, P3, P4 till, like, let's say P40. That is one target variable. The other target that they created was the delta between these two. So basically, P1 minus P0, P2 minus P1. So delta of 1 and even delta of 2. So these were some of the auxiliary targets that most of the teams created, and they were able to see that they were able to get better convergence, as well as like better scores also. So this is something that we missed, and we believe that if we had tried this, this would have increased our, like, improved our scores a little bit. And finally, coming on to the architectures. So the final model was a transformer only architecture, but there were multiple other things that we tried, and we started with what other people started with. Like, this was the common theme of this competition, that trying your sequential models, LSTMs and GRUs. And LSTMs worked till some extent for us, but post that we hit a wall on the performance, and we couldn't improve the performance of the LSTMs. Now, this was the case only with our team, I guess, because again, most of the teams were able to get very competitive performance using only LSTMs. Uh, Again, they were doing some nifty tricks like multitask training and very savvy augmentations, which we obviously did not do. Uh, Now, we also tried conformers, the original conformer paper which came out in 2020. We tried implementing that, and uh, again, maybe the implementation was wrong, but the performance was not there. We were not able to beat the performance of the transformer model that we have. And we also tried, like, experimenting with the combination of this, since we were already having, like, transformer and CNN combinations. We also thought that instead of CNNs, why not try LSTMs and transformer combinations? And again, these also did not provide the results that we were looking for. But the idea again here is that even though these didn't provide us the results that we thought they would, these helped us, like, think from different standpoints, and maybe we would be using these ideas again in some other, let's say, a time series competition. So that is how, like, I feel that these are the things, even though they don't work, this is the experience that you are looking for while competing in a competition. So Nikhil, would you like to add something here?
Yes. So, yeah, that was wonderfully said by Sahil, right? So, basically, in every competition, you kind of learn something new, right? And then you can apply it to different competitions, right? So, I get say messages from beginners which say, "How do we start approaching a competition?" Right. So this is like what Sahil said. You try to learn from the solutions of the past competitions, right? So you pick up a competition, you look at the winner solutions, you go through the data, try exploring the competition yourself, and then the ideas, the experience that you gather from the competition will surely help you do much better in the next competition, right? So I started as a beginner. I also did not have a clue, say, how to say, do such fancy kinds of tricks, or say participate in competitions and get a very competitive rank. But yeah, reading the solutions from other people and understanding the thought process behind the solutions helped me, improve and uh, come to such a point that we are I'm regularly getting good ranks. And maybe Sahil can also add a bit about his experience.
I guess if someone has any questions, we'll add then. So
Yeah,
yeah,
sure.
cool. So yeah, this is the end of the solution that we had. Um, we are open to questions if there are any. Thanks a lot, guys.
Yeah, hi guys. I'm adding the questions to the screen. So this is one question. Can you see it on the screen? Okay, so I'll read out the question to you. The question says the top solutions have all reverse engineered the PID controller. So like so were the neural network models that all the people are building, were they actually learning some patterns in the data, or were they only working as PID controllers? So that is the question.
So, so Nick, I would like to take this question. So, essentially,
Sure.
what you said was exactly right, and both the things are true. That
Hmm.
model is learning from the data, but the problem is in the data itself. The data was generated using it was a simulated data and not a real environment data. So what ended up happening was, even though the model was learning the patterns that existed in the data set, but since it was driven by a PID controller, we ended up learning that. So there is a beautiful explanation of this by Chris, uh, who basically visualized the impact that the change in UN values would have to the pressure profiles. And you could very well see that if you change the UN values by a certain value, there are a certain set of pressure profiles that you would be able to generate. So in the end, this model that I feel, given the uh, nature of the data set that we had, might not be able to generalize to a real world scenario. Now, another thing that happened was the values of RNC also, if you see, did not have any impact. Like in the end, it did not have end up having any impact. So even for the same set, like if you even change the RNC values, and if you trained your model deep enough, so that they were able to reverse engineer that PID logic, because the pressure is only dependent on the UN and the past UN, like the immediate previous UN values, the values of the RNC would also have not mattered much. So in the end, I would say that the models did capture what was there in the data, but because the data was generated in such a manner that it could be solved, maybe like the first and the second team did, they reverse engineered the entire data set by um, figuring out that it's a PID controller and reverse engineer the values. So yeah, so we could say that we were able to fit the data, but the data generation was something which could have been improved.
Okay, that was good to know. So there is another question which you have answered, but you can elaborate on it. So the question they asked is, did you try any LSTM on this data?
Yes, yes. So I think initially everyone started with LSTMs itself, right? So because LSTMs are much easier to train compared to transformers, right? So talking about our experience of training transformers, I think we struggled for a week for just training the transformers, right? So LSTMs are kind of the default thing you do when you have says sequential time series data, right? So everyone started with LSTMs, and I think you can see a lot of good LSTM implementations if you go to the public Kaggle kernels, right? So many people were using bidirectional LSTMs, right? So yes, LSTMs were definitely there.
Okay. Next question. So I don't think this question is for this competition, but it's a general question, I think. So the question asks, if you have a target set of 15 data points, is it good to predict one time step and appending it to train set for the next set of predictions, or to predict 15 data points at one go?
Yeah,
So yeah, Nikhil, please go ahead.
I'll just quickly add my view and then you can.
Yeah, sure.
Sure. So yeah, I think it depends on the data set, right? So I think I have seen such kinds of problems in multiple competitions where you have to predict multiple data points, right? So yeah, uh, this method where you have say a target of 15 data points and then predicting one timestamp and appending it to the train to for the next set of predictions, it's expensive. It's expensive in terms of computation, right? Because say you will have to train your model again, right? And say even if you don't want to train your model again, you'll have to redo the feature engineering process, right? But yeah, it might work well in certain scenarios. And predicting 15 data points in one go, I think it's a good solution in the sense that yeah, it's a good solution in the sense that you do not have to train multiple models, and say you can do it with the help of one model. And it's kind of the thing you do when you have, say, neural networks, right? So neural networks, you can easily predict multiple outputs, right? And say when you have sequential architectures like lstms or say transformers, right? So you can easily predict, say, 15 data points or 100 data points or 200 data points if they are sequential in nature, right? So I think, for me, I think it depends on the kind of problem, and then it's better to validate both the solutions, and then check like what works better for your case.
Yeah, so a couple of things here. So actually, the problem that you have asked for, like whether you should predict one at a time or all the 15 time steps, it actually depends on the nature of the problem. So what the first case wherein you predict one, feed the output into the next, and then you basically build kind of a auto-regressive routine. That is possible in case of like if it's a forecasting or a prediction problem wherein you are forecasting the values of the future, or it's a language translation problem. For example, that is a very perfect example wherein you predict the first token, feed the input into again that input um, uh, goes as an input for the prediction of the next time steps. Uh, this particular instance is slightly different because it's a sequence labeling problem, wherein you are given a sequence and you are given the entire sequence. No part is hidden out, and each sequence is independent of each other, and you just have to predict what are the labels on each time step. So here that auto-regressive component is something that you could build, but that is some that would not end up capturing some extra information that you won't be capturing in a sequence labeling problem. So both of these problems are slightly different. As I said, that in this particular case, even though you had to forecast the pressure values, but it was just a, a sequence labeling problem. You were given a set of UNs. You just had to label each of the UN with the pressure value that it would have. So it's not like you were forecasting something. So yeah, so both the solutions are possible in this case, but the auto-regressive solution, wherever the only, for example, a forecasting problem, there the solution won't work, wherein you are directly predicting those 15 outputs. So yeah, so there is a slight difference in the problem setup also.
Okay, cool. The next question, how to choose, I'll show it. How to choose how many data points to take for training and testing in case of time series prediction if we have less amount of data.
Nikhil, would you
Sahil,
like
you
to
want?
add?
Sure. Okay, so for time series data, firstly, I think to set up a validation, it's important that we replicate what we are expecting in the test data, right? So for time series data, say I'm expecting future values to test, right? So in that case, I think it's better if you set up a training and validation setup such that train data consists of past values and validation data consists of future values. One more thing that I've seen people do in different competitions is they directly apply k-fold instead of setting up a regular or say time series method where you have past values and you have the future values to predict, right? So in both cases, the best thing I feel you can do is you can have a holdout set, right? So say if I have 12 months of data and then I have to predict the next 2 months of data, right? So say for training I have data from January to October, and for testing I have data for November and December. So what I can do is in the training data, I replicate the test data, right? So I take the data from say January to August, I think, yeah, from January to August for the training part, and keep September and October for the holdout part, right? So these 2 months are acting similar to your testing data, right? Where you have 2 months in the future. Now with the training data, you can do as many experiments you think could work and then test your score on the holdout data, right? So instead of say having a regular time series approach where you train on the full data and then you just check your score on the holdout part, I can even do a k-fold this thing, right? So say what is the advantage of k-fold? I feel in this case is you basically are having say different model sets on different trained on different parts of the data, where you uh, and when you actually combine these predictions, they give you a kind of ensembling effect, or say uh, ensembling effect which kind of gives you much better predictions than a single model which is trained on the full data. Another approach I think which I have learned from Sahil itself was you use group k-fold, right? So in group k-fold you basically uh, keep some months of uh, data separate, right? And then you train on the whole data, right? So basically, your training and test data will not have the same months, right? So if I have 8 months of data, and if I'm training on say yeah, so if I'm training on say k-fold validation, the training and test data will always have different months, right? So if training data consists of January, February, March, then test data might say contain April and May, right? So I think the best thing to do is to set up a kind of holdout which is similar to your test data, and then you can try your experiments and see what gives you the best score on your holdout part.
Yeah. So one thing here, so since validation is something which is very, like, it is the most underrated component of the entire ML pipeline. Like when I even started out, I did not really understand the importance of having a robust validation scheme. Uh, so I started out with this misconception that a good validation scheme could help you score better. But the idea of a validation scheme is not to get great scores. It's actually to get an estimate of your model performance before your model performance is applied on an unseen data set. That is the underlying definition of a validations. Like, why would you need to do validation? And so given this idea, the idea behind setting up a validation scheme should be that you should be mimicking what will happen in your test data or your production environment. For example, I'll give you an example what happens when you're building out model in the real world. So generally, whatever data that would be coming in would be a data from the future, right? So that is like, even if it's a classification problem, be like any sort of classification, I just need to categorize my customers. Uh, in the end, the model that is going to run on a data that has not been seen by my model, and it is of the future, right? So I should be setting up my validation scheme in a time series manner. Why? Because my production data is going to look like that. It's going to be a thing of future, and that is why I would have to set up my validation scheme like that. Now, this is something that we might not do while doing competitions. Why? Because I'll give you two extreme examples. So imagine a scenario: you are doing a time series problem and you do a k-fold validation, and let's say you get a 90% accuracy on your data set, like a CV score, and your LB is also, let's say, um, uh, uh, LBs, I would say LB is close to 70%, right? You have your CV on a k-fold validation that you did, you have a 90% score, and your LB is around 70%. On the other hand, I did a time series validation wherein my holdout set or my validation set like um, were in the future as compared to the part I was training on. You get a CV score of around 68, and your score on the test set or on the leaderboard is around 67. Now, I would say that the second validation scheme is the right validation setup. Maybe from a competition standpoint, it does not make sense because you are getting better results with the 71 or using a k-fold validation scheme. Because in production scenarios, in real world scenarios, you would not have that test set. You would not have that future data that you could just peek into the future and see how would my model perform in the next 2 or 3 months. So getting a score of 68 is still better than getting a score of 90, because what would 90 do is, I would communicate that my CV score is 90, but in the end, when the model goes into production, you would see values of 70. Now, the entire decisioning by the product team or whatever team you are building the model for would have happened for that 90 score. but in the end you got only 70 on the in the coming months, and that strategy would significantly fail. So that is why I feel that your validation strategy should always mimic the data that is going to come, or that your model is going to see in the near future. In case of competitions, it is the test set which is hidden from us. But yeah, so this is something that you should always, like, this should be one of the principles that you should always operate on. Validation scheme is not something that you use to increase your score, but it's something that you need for a robust validation of your model. And it should be set in such a manner that it mimics how your test data is going to look like. And last thing, I'm blabbering a bit here, but one more important thing in this competition was, even though it was a time series competition, but if you look at the test data, it was not like I have, like, let's say my breath IDs are given. The data set, the test set was made in such a manner that so one way of creating a test set could be my first 40 timestamps of my breath could be in the training data set, and my last 40 timestamps of my breath could be in the test set. In this particular scenario, it would definitely make sense to go for a time-based validation scheme. Why? Because my initial set of breath patterns are in the train set, and the later set of patterns are in the test set. That means my test is forward-looking. It's into the future. But in this scenario, what happened was they did not have any overlap between the breath IDs. My entire 80 timestamps were within the train set, and in the test set, it might be that Nikhil's timestamps are present. So both of these did not have any correlation with each other. So that is why we could go ahead doing, let's say, a k-fold validation or a group k validation on your breath IDs. So yeah, so even though it was a time series problem, but the way the test set was set up, you did not need to do a time-based validation scheme. So yeah.
Okay, that's a great answer. There are a few more questions, so I will be putting this on the screen. One question is, what would be the most ideal way to deal with outliers in a time series data? So
Nikhil, would you
basically, how to
would,
detect and remove
so
outliers.
I'll go first. I'll go first. So, firstly, it depends on the nature of the model that you're using and uh, uh, the problem that you are solving for. So, let's say if I had a boosting model, or so I have frankly never worked in a problem setup wherein removing outliers has significantly boosted my performance. Apart from a couple of two, I'll iterate on those also. But let's say my modeling choice was a boosting model, right? Now, boosting models, what people try to do is they try to scale the data, they try to uh, remove outliers. But essentially, the way the tree is splitting, uh, it really doesn't matter if your transformation is a monotonic transformation, which in most of the cases it is, that you are not changing the order of the features. And it's prone to outliers because it's based on a splitting mechanism wherein a value less than or greater than equal to will decide your split. So even having those outliers won't impact your model performance that much. So this is one. If your model of choice is such that it's a tree-based model, I would say just ignore these things. But on the other hand, if it's a neural network model, we have heard about like normalizing your data, and the underlying idea behind normalization is it helps us to create a smoother loss manifold, which helps us to converge the data faster. Again, in this competition also, we did not really remove any such outliers. We did certain normalizations, and that worked out well. In case of regression problems, what you need to be careful about is, so this will not really impact how your model learns. But let's say there are outliers in your target values, not in your input values, but your target values. And let's say my I had 1000 data points, and of those 990 data points were in the range of 0 to 10, right? And just the 10 data points had values more than, let's say, 1000. So these essentially are my outliers from a target standpoint. And if you just build any model, you would see very large values of whatever your loss metric would be. So in this case, you might end up seeing you if so the basically the estimate of performance that I'm getting from this could be a lot higher from the actual estimation that the model might have. So in this case, it might be helpful if you remove those outliers and uh, see your model performance. Now, it also depends on the reason why these outliers have come into your data. For example, if it is some bug in your application, or let's say a bug in your data collection strategy, then you should definitely remove. But let's say it's a common theme that occurs every certain at a certain periodicity, then it would be advisable not to remove those outliers, but rather to build in features in your model, or build such features that would help us capture those outliers. So it actually depends on the source of your outliers. And yeah, so in most of the competitions you are fine if you don't remove outliers, but this is not to understate the importance of EDA. Like, EDA will help you understand if these are outliers which are solely results of data errors, or data collection processes, or these are something which we need to take care of in our feature set.
Exactly. Yeah. I'll just add to the last point that Sahil mentioned, outliers for feature creation, right? So, say supposedly you have a scenario where you are trying to uh, say predict the number of units a shop will sell, right? So basically you basically see on most days the sales are in the order of hundreds, say like 120, 130, 140 for say any good, right? So it could be any good, but the sales are around hundreds, right? But say for 6 or 7 odd days you see that your sales have bumped up in the order of thousands, say maybe 1000, 2000, 3000, 4000. So say instead of removing this, you actually want to expect why this happened, right? So one case I found out working with such kind of problem was that it was because on those days the shop had some kind of sales and offers, right? Maybe because due to there were some holidays or some festival seasons going on, right? So maybe you can use this to actually create some more meaningful features into your model, right? So maybe your model can expect that on holidays or say promotional days you can have a bump in the sales, right?
Okay, that was
Yeah.
a great answer. There are a few more questions. This is a question. Suppose we have a competition that has given simulated data, but just to increase the data set size, we add some data from another competition. What should be our approach for doing cross validation there?
Cool. So uh, I'll give it a go. So
Sure.
so again, the idea behind validation scheme is to mimic what is going to happen in your test set. Now, as you mentioned that there is a competition here which is going on, which has given its own data, but you also feel that some external data could be useful, right? But the test set is not going to include those data points, right? So the best way of doing this is like, you include this additional data. You do your validation part on the existing computation's data only. For example, let's say you do a five-fold cross validation scheme, and you had 10,000 data points, and within each fold you have 2,000 data points. Now you found another data set which had a data set size of 20,000. Now what you would end up doing is, so in case there is no additional data that I found from other data set, you would end up training five models wherein the data training size would be 8,000, validation size would be 2,000, and you repeat this five times. Now, in case you find another data set which is of size 20,000, you add it to the train set. You do not change your validation set. Why? Because in
Hmm.
the end, your score is going to be calculated on the validation, on the test set, which is only from this competition. So if you could do it both ways also, but it is recommended, since your validation, the idea behind validation is to mimic what is happening in the test set, include the additional data in the training part of your validation schema, not in the validation part. Yeah.
Yes, yes. I'll just add to it. So maybe not from the perspective of cross validation, but if you want to use external data, what you can do is you can basically apply the approach of transfer learning, right? So say if you want to make your model learn, say some more same model have a good initialization, right? So basically what we do in transfer learning for images, right? So we have trained a model on a very large data set, and then we try to use the same model to predict on smaller data set, right, for some specific kinds of targets. So that is basically what we are doing, right? So we are using the model trained from some other data set and applying it to this model, right? So you can be more creative and you can actually apply it to even time series competitions, right? So maybe you can train your model on, say, some different times series data, right? So which has, say, some similar characteristics to the problem that you're working on, right? So maybe your model can have some good initialization points, right? Good starting points, and from there onwards you can try training your model and see if your performance improves.
So
Okay,
if you want to
interesting.
see this
Yeah.
this current implementation, there is a competition going on for Indian NLP. There's a competition
Hmm.
called Chai. You could see this approach being followed there, that people are using external data, pre-training on that, and then training on the data set that is given in the competition. Yeah. So this is a very fruitful approach. Like the entire concept of transfer learning is based on this.
Okay. So there's another question. What motivated you to increase the folds number? I mean, what caught your eye to do that? Was there a significant difference that you noticed?
So
Yes. So
yes, Nikhil, go ahead, please.
sure. So yeah, so what caught RI was the validation scores, and most importantly the leaderboard score, right? So it's yeah, so a leaderboard score is basically a joke, but yeah, if you have a good validation setup, and you can check your model's performance on the validation setup, then you go for the setup which actually maximizes your validation performance, right? So like Sahil mentioned, once you have a good validation setup, then your basically the objective becomes to do something that maximizes the score on that validation part, right? So we tested it on the validation data and we saw that we were getting improvement, right? So once we saw that we were getting improvement, we went from 5 to 7 to 9 to 11. And I think by the time people on Kaggle discussion forums had also mentioned that training on the whole data is really helping boost the performance. So that was not even a question of 15 folds, it was a question of 15 seats then.
Yeah. But again, like this is from a competition standpoint. I would still suggest that you should not look at like increasing the value of k increased your performance. Yes, definitely you should try this in the competitions, but this is not the underlying theme of validation. This is something like which is very important to understand. Yeah.
Okay. So there is a last question here. Thoughts on applying knowledge graph based approaches or geometric learning methods? Maybe replacing the learnable front end with a knowledge graph or using learned embeddings into graph neural networks or GATs.
So again, the question, like the problem that we were given did not have that embedded bias which required us to sort of use some sort of GNN. So I'll give you an example of a competition we did last year. So there was this COVID vaccine competition, which had a linear data similar to this, but it had a nucleotide sequence. That means there was a DNA sequence, and since we all know DNA has an embedded graph structure in it, therein we tried to use GNNs. We basically built some message passing network there, and it helped us improve the feature extraction process. But the idea, so all this seems very fancy. Like, why not apply, let's say, a GNN? Why not apply, let's say, some graphical model, or even in our case, why did we apply transformers? It all begins with the bias that you feel you have in your data set. For example, images have this embedded bias that the features of the nearby pixels or the nearby pixels would help us really predict what is happening at a given pixel. Like the nearby values would impact the score a lot. Um, Sequential models work very well on text data. Why? Because there is a relation between, like, there is a sequential relationship between text, not a spatial relationship. Similarly, given the let's say a social network problem, there is a graphical bias there. Like there is a graphical relationship between the nodes that is present. So you could have applied here, but in the end, you would have ended up learning a linear dependence between the data points, and that is what essentially your transformers or your sequential models would end up learning. So given the problem data set, it is very important to identify what is the inductive bias within that problem data set. That will also help you choose the type of model that you would end up using. And in this case, like, it did not make sense for us to use any graphical models. But having said that, there are many competitions on Kaggle which have happened, like the COVID vaccination. There is a graphical nature to the DNA structure involved. There was a molecular prediction competition which happened in 2018. That also had, like, we had to predict chemical properties of a given a molecule structure. Now, since again there was a structure, there were small graphs. So again, the best performing solutions were graphical. There were GCNs were like message passing networks were the winning solutions there. Having said that, you could also, so there's this, if you want to read up, this is just solely from a reading standpoint. There was this competition of NFL prediction which happened in 2019, and there was this beautiful solution by a famous Kaggler called CPMP, graph transformers. Now he basically infused the concept of, basically he introduced the concept of graph attention, or you could say an attention layer which is not driven by the fact of like having a multi-head attention, but rather he introduced a bias which captured the graphical nature of the data set. So again, you can play around with combining these different approaches, but it all starts from understanding what inductive bias does the data have.
Okay. Understood. That was a great answer. There are no more questions, I think. So I think we'll be ending the session here. Yeah. Thank you so much, both of you, for attending this talk and giving us so much insight on this competition. I hope all the viewers learned quite a lot, and we'll be conducting these in the future as well. Also, just an announcement to everyone who is watching. On the screen, you can see the Discord link. This is the community that we have created, and we want to create this community for beginners where they can come in and ask questions, clear doubts, help in whatever competitions they need, form teams, and everything. So join in here if you're interested. This is the community. We'll be staying here. I'll be pinning the message as well in the chat section. And Nikhil and Sahil, thank you so much for attending this talk. And
Yeah.
Thanks a lot,
we're ending
Abranta.
right now. Thank you
So
so much.
Thanks a lot,
just
Abhinav.
Yeah.
like what you are doing is like, it's a really great initiative, and when I guess I started out, something like this was really missing. So kudos to that one, man. Like, it's a great initiative by you guys.
Thank you so
Yes,
much.
yes.
We'll be continuing to do this in the future as well.
Sure.
Yeah.
Okay.
Yeah,
Thank
definitely.
you,
That was a
guys.
really great initiative. Thank you, everyone. Thank you, Sahil, for attending. Okay. Bye.
Thanks.
Thank you, guys.
Bye
Thank you,
bye.
Nikhil,
Bye.
and thank you, Sahil. Bye. Bye, everyone. Thank you, everyone, for attending this talk. We'll be ending now. So have a good day. Join the Discord community. We'll try to help you out whenever we have opportunity. We'll be adding people from the industry as well. So if you guys want any opportunities, if you guys want helps with any competitions, if you guys want to form teams, then you can join in this Discord community and try to keep it moderated because we'll be moderating as well. And I hope this stream was helpful for all of you. So thank you so much for attending and bye.